Hello everybody, I'm Li-Feng from Southeast University, China, and it's my pleasure to present a lecture about mutual inductance suppressed stacked inductors for passive wireless multi-parameter sensors. It is the outline of my lecture, and it consists of the introduction, design and simulations, experiments and results, and the conclusion. First comes the introduction. The LC-type passive wireless sensors are widely studied to monitor parameters of interest in situations where wired connections are difficult or even impossible, such as pressure, strain, temperature, humidity, threshold, and pH. They provide their advantages in low cost, small size, long lifetime, and the feasibility of installation. The LC sensors usually consist of an inductor and a capacitor. The capacitor or the inductor, or both of them, change as a response to the parameter, resulting in a shift in the resonant frequency. The resonant frequency of the sensor tank is determined through the readout coil impedance or input return loss, the S parameter. The existing LC sensors are limited in applications for simultaneous detection of multi-parameters. An array of LC sensors would overcome this problem in price of occupying a large space. For the sake of saving area, the inductors can be stacked up. However, due to the mutual coupling between the inductors, the signals would affect each other and the resonant frequencies will be shifted or even missing. So the question is how to suppress this mutual coupling, and this is also our topic today. The proposed structure of planar inductor is in a specific winding to achieve the minimized inductance. The rotation direction of each loop is opposite to the adjacent ones, and there must be even turns. Take this inductor as an example. The first loop is anti-clockwise, the second is clockwise, and the third is anti-clockwise again. The rest can be done until to the sixth loop. In a multi-sensor system, the inductors can be stacked up, and the capacitive sensors are linked to the corresponding inductors, forming LC circuit. Here are two coils, both consist of two loops in the proposed structure. The side length of the coil is L. The separation between adjacent loops is S, with the condition that L is far greater than S. The two coils is coaxially aligned at a distance of D. According to partial inductance theory, when D is M times of the S, for two coils both consist of N turns, the mutual inductance between them can be calculated as this equation. The mutual inductance will be 0 when M becomes very large, and the mutual inductance becomes greater when the distance between two inductors is reduced and reaches the maximum when the distance is equal to the separation S. To validate how the interference between the resonant frequencies, the software ADS was used to make simulations. Here is the layout of the inductors, and the relative parameters are listed here. 3 inductors are coaxially aligned, and there is also a readout coil to capture the resonant frequency. 3 variable capacitors are linked to the corresponding inductors. Then the three capacitors are changed in turn to observe the interference between these 3 resonant frequencies. First, capacitor 1 was changed, and capacitor 2 and capacitor 3 was staying constant. Frequency 1 is corresponding to capacitor 1, and frequency 2, frequency 3 were corresponding to capacitor 2 and capacitor 3 respectively. It is apparent that frequency 1 is increased from 38 to 43.5 MHz, while F2 and F3 were staying constant. Then capacitor 2 was changed with capacitor 1 and capacitor 3 staying constant. There is no offset in F1 and F3, while F2 was changed as a response to capacitor 2. Finally, capacitor 3 was changed, and capacitor 1 and capacitor 2 was held constant. We can see there is no offset in F1 and F2, while F3 was changed from 84 to 96.5 MHz. It is then confirmed that interference between these three resonant frequencies can be suppressed, and the three resonant frequencies can respond to the corresponding capacitors. To demonstrate how the proposed structure in the applications of multi-parameter sensing system, 3 inductors of the same size was fabricated in a multi-layer PCB. 3 capacitive sensors for temperature, pressure, and humidity were connected to the corresponding inductors, forming 3 LC circuits. The temperature sensor is based on silicon oil, and the relative dielectric constant can respond to the temperature and hence to the capacitance. The relative humidity sensor is based on graphene oxide, and the relative dielectric constant can respond to the humidity. The pressure sensor is a commercial product, which is a silicon absolute pressure sensor. The pressure is proportional to the bending of the diaphragm and hence to the capacitance between the electrodes. For humidity response, the relative humidity ranges from 15% to 90% RH, while the temperature keeps at 25 degrees Celsius and the pressure is 100 kilopascals. F1 is corresponding to humidity and F2 is corresponding to temperature. F3 is corresponding to pressure. We can see from this figure that F1 is increased from 45.5 to 49.5 MHz, while F2 and F3 stay constant. The sensitivity of the humidity sensor is about 53.3 kHz per percent RH. Then the temperature ranges from -20 to 100 degrees Celsius when the relative humidity keeps constant at 50% RH and the pressure stays at 100 kilopascals. There is no offset in F1 and F3, while F2 was changed as a response to the temperature. The sensitivity of the temperature sensor is about 41.7 kHz per degrees. Finally, the pressure varies from 50 kilopascals to 110 kilopascals, with the relative humidity at 50% RH and the temperature at 25 degrees. There is no offset in F1 and F2, while F3 was changed from 89 to 97 MHz. The sensitivity of the pressure sensor is about -133.3 kHz per kilopascals. The measurement results above validate that interference between the three frequencies can be suppressed, and temperature, the humidity, and the pressure can be monitored by their corresponding resonant frequencies. Simulations and experiments validate the 3 specific winding inductors proposed have no apparent mutual inductance. Experiment results show that the 3 resonant frequencies of the 3 LC sensing circuits had no apparent interference while sensing the environmental parameters. Inductors in the proposed structure can be added to more for more parameter monitoring. That's all. Thank you.